Hello, friends. Welcome to episode 4 of Kermit GNC. Let's build together. A key philosophy to drive home. At this stage, we are not coding features anymore. We are doing actual flight test and validation. Every test should answer one specific question. Did the aircraft respond in the way real aerodynamics predict? So, today, what we will cover yaw stiffness, so end roll due to side slip. These two are tied up with side slip angle beta. If you remember, we never used beta before this. So today we will connect beta with our derivatives. We will look at some of the side slip specific things like some errors we have made in the past, which I will point out. I forgot to earlier, and we will fix those. And let me assure you, those didn't affect before because we never used those until now. And another important thing is we are going to wire control inputs into the model. So we will add thrust, elevator, aileron, and rudder. And in the end, we will do some lateral dynamics analysis and testing. So let's get started. We stopped at this stage in the previous episode. So if you have not gotten a chance to check that out, the description is below. Please do check it out before you start here, because this is a continuation of the work we have built so far. That is quite an achievement, isn't it? And yes, this does feel fruit worthy because these dynamics models are not easy that you can build in one sitting. They are complex. You add more and more and more and more every single time, and it builds up on top of each other layer by layer. So let's get started on our modeling. I will do some cleanup, some more cleanup, so to speak. So let me give you some more tips today, which will help us to get rid of these go-to tag visibility blocks and also these from tabs and clean this area up quite a lot. What we can do is the VB, if you click on this, you see it highlights this one, the source it gets its signal from. So this is the go-to. If you double click on that, the tag visibility, turn that into global, and this global tag visibility actually does miracles. So we are going to switch all of these into global visibility to reduce chaos. What local visibility does and what scoped visibility does, I have covered those in the previous videos. So another reason to check out my link of the previous videos below in the description. All right, so this is global right now. Let's do the same for Euler angles. Double click, global, apply. This PQR, it is global, checked. Now let's come to this side. I will get rid of the VB, Euler, and then these wires and these input links, so to speak, as well. Okay, let's go inside the aerodynamic subsystem now. You notice this is red highlighted, this is red highlighted, which means the things I deleted were actually being used at these two locations. So what I will do is I'm going to instead use a from block. And if you single click on that name, you will see a drop down of all the options available for you. So I will choose VB because that's what was connected here. And I'm going to do the same thing on top here. So from block, single click on that A character and choose Euler, because we were using Euler to get our gravity force subsystem built up right there. So that takes care of that. And let's go back to the top level. Alrighty, PQR, we changed that. PQR is used here. So we can actually delete that, go inside the moment block, and this PQR here, double click on it. And if you update tags, you see the yellow highlight. That means it got updated to the newer system we are trying to establish. So that is not a problem anymore. I will do the same for the rest of these. And if you remember, these four come from inside the aerodynamic block set or subsystem. So I go in there one more time. I double click on this S go to block. I reduce the visibility from scoped to global. apply. If you notice, it's so unique. These symbols or blocks have their own way of telling you expressively the changes. For instance, whenever you set your tag visibility to be scoped, you see the curly braces around the name. That's how you know it is scoped. But if you change to global, that's gone. Isn't that so clever? I know. Another reason I like MATLAB Simulink. I've been using this software for about 5 years now. So, yeah, every day you just learn more things about it that makes you fall in love with it. All right, another one is alpha right there, global. Okay, I believe we took care of everything. Let's go around to do a quick check. All right, looks good. Let's get out, delete these. Now go inside of the moment subsystem and let's make sure everything is fixed. So Q bar, double click, update. Okay, yellow highlight. S, update, yellow highlight. Alpha, update, yellow highlight, and PQR, we already did that, and vSafe right there. Update tags, yellow highlight, that means it's confirmed that everything is switched. And check this out, beautiful. Cleaner than before, gives me more room to add my controls, which is coming up next. So to do controls, I'm going to double click on an empty spot, type slider. I am planning to use sliders to design my control systems, just to replicate an actual cockpit control system we have, where you get like yoke or stick, you get throttle, and you get rudder pedals. So they give you a range of motion, and I wanted to capture that realistic experience. Another good thing, or another good reason to use the slider block, is later you can just swap these slider blocks and connect your control inputs directly to devices like joysticks or rudder pedals or throttle input, actual devices. So we will navigate those in the future. You can also hook these up to other flight sim softwares and run this along with the devices, along with the flight sim software, to get an actual flight simulator experience. Those are future scopes with Kermit GNC. So tune with us if you plan to see them. For now, I am putting some constant blocks because the slider block actually needs some other block to connect to. Otherwise, it doesn't establish the connection. So let me name them. I will say THR. Actually, let's just call it throttle because I want to preserve THR for the output signal out of these. Let's call these del E, del R, del A. If you click on one of these sliders, you will see this connect button. Click on the connect button, the screen turns gray. You select whichever block you want to connect to. So I'm going to select this constant throttle block. It gives you a pop-up. Select that and you see connected to throttle value, and the name throttle appears on the top. That's how you know the connection got established. I will do the same for these rest. So connect, del E, select del E, connected, name appears. Next one, connect, del R, select del R, connected, and the name appears. And last one, del A, select, connected, and the name appears. Once you are done with all of them, you can click or hit escape and everything is white again. Now let's put the ranges or limits on these. So I want the ranges to be, let's see what this block parameter is. Oh, it's the throttle one. I don't want that. So I want these ranges to be, let's see, throttle, I want to have that as a fractional lever. So this is 0 to 1, and I want to make this bigger so I can see the values clearly without any interruption there. Del E, Let's call that for the elevator for a Cessna-like airplane, -25 to 25 should suffice. For rudder and aileron, -20 to 20 is a decent amount. There we go. Perfect. All right. So if you noticed, these values are in degrees, and so I want to convert them to radians, right? So I will double click, I will write degrees, and degrees to radians is another block that will appear, and I'm going to give the same to the other two as well. There we go. Perfect. For the throttle, I am going to use the throttle formula. Let me put that formula. As you know, I always like to show you guys the formulas I use. And so, it's always a good way to verify yourself. If something is not connected properly, then you can always use the formula to fix yourself. Goes a long way. All right, this is what I'm going to do. This throttle is the fraction coming from here, and then I need a maximum throttle power, so I will use a gain block for that. I will call that to be, 2500 is a decent number, and let's make it bigger so we see it. Tad bit more. There we go. And you can call it Tmax. And let's connect them to, that will give me my, I'm going to use a go-to block to capture that signal. And this is actually my THR, throttle value. Double click on this to make sure your visibility is global, and also to make sure that your tag name is inside as well as outside. Okay, let's see what it says. Duplicate go-to blocks with same tag. So, okay, so we will see how we can fix that. Duplicate go-to blocks with same tag. I wonder. Alrighty, that shouldn't be a problem for now. Let's see. I want some more go-to blocks. Or I know what I did. Two more. Let's keep going. I thought I knew it, but that looks right. We will see. We will see. It's part and parcel of doing these modeling. Things are gonna break in the process. Things are gonna not work, go wrong, but that's not to worry about. What you wanna make sure is, once this software gives you the error message, or these kind of red highlights, or it just doesn't work, the graphs will look weird. So you want to know how to read those error signals and capture them in time or before time, and decode them, and map them to the root cause, then troubleshoot. If you know those things, if you enjoy doing that, then you will love this. Alrighty, so let's see. Del E, tag visibility global. Well, that fixes that. Let's do the same thing for the rest of these. Del R, tag visibility global. Del A, tag visibility global. Okay, so all right, once we are through this, let's make sure everything is good. Another thing I want to show you is how to select the values. So if you just do a click on any of the slider, they will make that slider active, and it will highlight the corresponding constant block. Now, if you just click at any of the values you want to choose, let's say 0, that will show up here. Now, it doesn't show up right now, but if I click on this C twice, you will see that number. But just because that number is way too big to fit inside this box, it's not showing it. If I make the box bigger, it will, but I am not concerned about it, so I'll just leave it like that. Alrighty, so that takes care of my controls. Now, let me point out some of the errors I was talking about that we missed earlier, but no problem. We can fix them now. because now is when we are going to need these parameters. So coming down here, I'm going to zoom into it. This beta, the beta formula does sine inverse of v, little v over capital V, which is my v airspeed. If you'll notice here what we did earlier, this is connecting to U and this is V, which is not correct. So let's delete those connections and let me connect this to the little V. And then I need a V safe here. So let me get a from tag, click on that A, and let's find our V safe right there. And I will hook that up. That takes care of that mistake. And then I can get rid of this terminator now. I want a go to block because I want to get my beta out of this, since we will be playing with beta now. So I'll just call it beta, double click, same name, beta, tag visibility, global, apply, and OK. Alrighty, that's that. Another big thing I want to show you is if you go across to the right, over here, my drag force, it was a -1 gain. It needed to be a -1 gain, which it is now. It's all fixed. But on one of the initial episodes, when I set this up, I accidentally left the gain to be 1. So that... again, that needs to be a -1, but we did not do any major analysis at that point. So it's fine that we are capturing it now. Okay, if you see any other thing, do comment below so we work together as a team to get this thing built up. All right, so we designed all these 4 controls. Now, where do we put these controls is the key question. So I go inside my aerodynamic block, and I will, if you notice, another advantage of having these formulas, you see, this is my Fx, meaning the Fx vector of my F force vector, or Fx element, which is the first element, that has a T in there. That T is for throttle. So let's put that now. So this is my first element connected to this sum block. You double click on that summer, add another plus sign there. That will give you the channel to connect, and then do a from tag, rotate it. Control plus R is for rotation. If you click on that A, it gives you a drop down of all the available signals, and there is your throttle. That takes care of the T there. All right, now let's get out of this. Throttle is connected now. We want, let's go inside the moment subsystem, because all these other 3 will connect via the moment coefficients. So these were our pitch, roll, and damping coefficient that were in a way giving us our, roll moment coefficient, pitch moment coefficient, and yaw moment coefficient, which were CL, CM, and CN. Now I am going to have updated formulas for those, and this is completely normal. You start with the rudimentary formula you have at that stage, which we had earlier. We were only accounting for one specific parameter of it, the roll damping, but now I want to add more, so I update my formula. Now, if you notice, this corresponds to the middle term, meaning I am responsible for adding the first and last term now. So let me put these formulas first so you have them inside as to what I am planning to do next. No, I want to make that large, like that. Okay, that is the new formula for CL. I need a new formula for CN, which is that. And we need our updated formula for CM, which is that. Okay, that goes there. Okay, so these parameters are going to help us to connect our del E, del A, and del R, as well as our beta. Now, one cool thing to notice here is if you look, the beta is appearing both for roll and yaw, which means beta is the common link between these two, which accounts for the roll-yaw coupling, which is pretty famous in lateral dynamics of airplanes. So let's do this connection first. Let's see, where is CM? Let's take care of the pitch damping since I have only one term to add there. Two were already existing. Pitch damping CM, which I see right there. If you don't find it, you can trace back. So you see M pitch, which was my MY, is here. That has CM. So the fourth channel here is CM. You trace back, it brings you here. So the summer was taking care of two of the terms. I will just double click on the summer, add another plus. That will give me an open channel for the third term. And what is my third term? It is CM del E times del E. And del E is the aileron, or sorry, the elevator deflection, which is one of my controls. So if I do the drop down, here is del E. I click on that. I'm going to rotate my block. So control plus R, and then I will use a gain, rotate that as well and connect that. This gain is going to be my CM del E. You may ask, what is CM del E? CM del E is elevator effectiveness. So the term responsible for elevator effectiveness, meaning you ask how much pitching power my elevator of the airplane is going to have. So this will take care of that. For now, let me put it to be -1. Okay, these parameters, again, these CM del E, CMQ, CM alpha, these are the meat of this entire modeling. These are your parameters you end up tuning for specific models of airplanes. If you don't have these well tuned, you may not even pass those certification requirements that FAA has for these. So that's why this is a massive task, tuning those, other than modeling, of course. But once, like, modeling is understanding physics, aerodynamics, modeling the whole thing is, I would say, 50%, and tuning these parameters and taking care of the right values and predicting the scopes, that is another 50% of GNC modeling, in my opinion, of course. So that takes care of CM. Let's do CL. For CL, we need two more terms, the beta term and del A term. So let's find CL first. There is CL there. Let me place them here. Let me see where it goes first of all. So CM is directly connected to that channel. Let me delete that, put a summer here. So you do sum, double click. I will place a third plus sign because I do need 3 of them. Now, first one can just go directly to the existing CL term that was there, or part of the CL term. All right, these two are open. Now let me grab 2 from blocks. That's 1 and that's 2. I will say this one to be beta and set this one to be del aileron, del A. Okay, let's give 2 gains for both of them. Okay. All right, this gain, you can zoom in to see better. All right, this gain is going to be my CL del A. This is aileron effectiveness, as in how much rolling power you want to give to your ailerons. And this one is, I want to give some room there. All right. CL beta. Okay. CL beta, the dihedral, and that connects to beta. Let's connect both of these. I did take care of both pretty well. So there we go, like that. All right, now we do the CN. CN is gonna also need 2 terms, but I already have beta here. I can reuse that. So I need only 1 from block, rotate that, and we need del R, another gain for del R. And this gain is going to be my CN del R. And let's leave some room here because I want to bring that beta But before that, this is the CN channel. Get rid of it, put a summer, just like we did for the aileron. Double click on it, give another sign, plus sign, and then connect the original one, connect this one back to it. All right, and this can go to one of them. And yeah, and then we need another gain. I will rotate it downwards like that, and I will connect that to beta, and this will go here. The name for this gain block is going to be CN beta, or just CN beta, like that. Okay, so now we want to add the values for each of them. So let's do it carefully, one by one. Cn del R, that is your rudder effectiveness, how much yawing power your rudder is going to have. Let's give a positive 0.08 for that. I don't see it. I'll need to make it bigger so I can see. All right, that is good. C and R, that's another error I was talking about. C and R was positive earlier, but if you recall, I want to make C and R to be a negative. So this can actually match with my expected results from the plots. Sometimes your Euler angles six-off block may be considering a different sign convention on the background. So there's the only way you can fix that is you look at your plots, you play with this, you run the analysis, you look at the analysis. If there is a sign difference, then you know you come here and you fix this. Also, CNR over here, if you notice yaw damping, that has CNR, and that is responsible for helping in damping the yaw behavior. So we want that to be negative, so it can help in damping the yaw signal. Okay, so that fixes that. Let's keep going. So Cn beta, that will be negative 0.1. Okay, let's go to Cm parameters, and Cm del E is -1, and everything else looks good. Cmq is -2, Cm alpha is -0.1. That would do for now. Let's look at the roll factors. So Cm del A, let's make that 0.1. And CL beta, let's make that -0.08. How did we get these values, or how did I get these values? Again, you do some research, do some lookup. You can very well use flight dynamics data. If you have those, you can use those flight dynamics data to get some plots out of them, and you can use those plots to get these values as well. But if you don't have flight dynamics data, you can take some dummy numbers and start from there. So that takes care of all of these. Let's go back to the top level and let's make sure we have accounted for all of the things on our agenda before we do some testing. All right, so we put Cn beta times beta yaw stiffness. We put roll due to side slip Cl beta times beta. We did fix the sign for all of the side slip parameters, and we added the 4 controls, which is the big part about it. So now let's go back to our Simulink and we will try to run this. So let me do the Aileron authority test first. How I will do that is I'm going to double click on this 6-off block. I will make sure that I have some initial forward velocity u. 30 is good enough, but everything else is 0. I do not want to start with an unusual attitude that I don't want. So I will set everything else to be 0 besides the mass, of course. Over here, throttle, you can use max power. I'll just keep my throttle at 0.8. Why not? For del E, I'll leave it at 0. Del R, leave it at 0. Aileron is, I want that to be about 10 because I want to do aileron effectiveness test. So I want some aileron. So I gave the aileron of about 10 degrees. Now let's do the, let's run the Simulink. Let's see if it will work. Perfect. No error messages. Now, when you do this, be prepared. If you see error messages, be prepared to troubleshoot from that, like I was explaining before. All right. Since this ran, let's take a look at the Euler angles block. So this is what I get for about 30 seconds of it. Looks like the middle one, which is responsible for theta pitch angle, is staying pretty stable. I gave aileron input. I'm expecting some roll. So this yellow one is my roll, and I do see some changes happening here, which is what I expect. So that is giving me a positive aileron towards the right wing, which is what is expected. So that's good to see. These white or these vertical line jumps, don't worry about them for now, because these are coming from the Euler angle wind up. So that is normal. Or Euler angle wraparound, so to speak. And that is normal because Euler angle, the way the physics and math works in setting up Euler parameters or Euler angles, it has its own limitations. It does have some wraparounds at times, but in the future, when we swap that 6 TOF block with our own dynamics, that should take care of that. So ignore that part for now, nothing to worry about. But if you look at the other things, it is showing change, big change with the roll. But what's unique is this is also showing you the coupling I was talking about, the rudder to aileron coupling, or yaw to roll coupling, or roll to yaw coupling. This orange one is the psi, or your yaw angle, and that one is also changing, but we did not give any yaw input in this, and that is because of the coupling happening. So that's a good thing to see. Let's do a quick check for the rudder effectiveness. So I will come here, I will give some rudder input about 10 degrees, and I'm gonna give the aileron 0 input this time. Now let's run this again. All right, let's show you the graph. All right, Euler angles back again. You see the elevator blue one is staying pretty stable, but this psi or yaw angle is showing deflection how I want it, and then the coupling is also showing deflection with the yellow phi angle, or your roll angle. So that is expected behavior, and that is your coupling taking care of it. So that's some of the lateral dynamics I was talking about. And yeah, that's what I have for today's episode. Hope you enjoyed it. I will see you next time with some new content.